So let's now look at an example of finding turning points and characterizing what they are, diagnosing whether they're maximums or minimums. Okay? So in this question, you asked to find the coordinates. That's immediately underlined because you'll spit out x values as part of your calculations, and this is just saying they want coordinates. So you'll need to work out the corresponding y value. So as soon as you get your x value, you need to plug them back in to work out what the corresponding y value is so that you're actually answering the question. So it says, find the coordinates of any stationary points on this curve. Okay, and distinguish between these points. So stationary points immediately makes me think dy dx is 0. So that straight away necessitates that I'm going to need to differentiate y. I'm going to need to have an expression for dy dx. So I differentiate this simple expression here, and I get dy dx is this thing here. Okay, so at a turning point, the gradient is 0. dy dx is 0. So I'm going to set this equal to 0. Because it's a quadratic, it factorizes up all nicely, and here I get two x values. These x values here are the stationary points. At this stage here, you could plug these back in to find the y values, and you've definitely found the coordinates of the stationary points. We just need to diagnose what the kind of points they are. So here, I've got my two x values. I end up actually just working out the y coordinates a bit later on. But for now, these are the two x values I'm dealing with. So there might be maximums, there might be minimums, there might be points of inflection. At this stage here, I'm maybe being a bit naive, we'll see why in a second, but I don't know what they are, so I'm going to try and work out what they are. So I know that my main tool for deciding whether something's a maximum, a minimum, or point of inflection is d squared y dx squared, which means differentiating dy dx again. So I differentiate this again, and I get this expression here, and I get 6x minus 4. This is the thing which, when I plug into it, will tell me whether something is a maximum, minimum, or point of inflection. Unless it's 0. So I first of all try this value here. I get that d squared y dx squared is minus 8. Minus 8 is less than 0, so this is a maximum. This point here is a maximum. So the only thing I need to do then, which is what I did down here, is I found the corresponding y value. So minus 2/3, 40 over 27, that is the x and y coordinate of a maximum. So then I begin to look at the next one, x equals 2. I plug that into my d squared y dx squared expression, and I end up getting a positive value. So that means it's a minimum. Okay, I've got the x value being a minimum. I plug back in to find the y value, and so I get this other coordinate here. Now, this would be a very, very generous question to get, and the reason is that we know what cubics look like. A cubic with a positive x cubed turn has a basic shape like this. Now, it doesn't matter where I position this. You might be a bit worried that I've not really thought about where the turning points are, where it is. It wouldn't matter how I drew this. I could draw one of these kind of ones up here. I could draw one where it just, that was supposed to just touch there, but that kind of shape there. Okay, but I know if you've got a positive x cubed, I know that you're going to get a maximum and minimum, and I know that you get to the maximum first. And everything here in this whole question bears that out. I've got two turning points, and the one that happens sooner, the kind of earlier x value, kind of it's a negative compared to a positive, this earlier value here at minus 2/3 is a maximum, this one's a minimum. Okay, now don't get confused by the size of these values. Maximums and minimums can happen anywhere. As long as the value of this is higher than the value of this, you're okay. I mean, there's other ways you can think about this. If you try and draw a graph, anytime you come across a maximum, you can't have another maximum after it. I mean, just try having a maximum followed by a maximum. There's a maximum. Well, to make it a maximum, you have to go down a little bit. There's no way of getting another maximum without doing another turning point in between. So once you get one maximum, you know the next one must be a minimum. There are lots of nice things here. I mean, anytime you've sketched graphs, you've maybe begun to notice the patterns. You know, cubics have two turning points. If you wanted to draw a quartic, well, in general, a quartic has 1, 2, 3 turning points. Sometimes these can merge together to give you fewer, in the same way that sometimes a cubic can merge so that the two turning points sort of come together and you get that classic x cubed shape. But the maximum number of turning points you can have for a curve is one less than its highest power, than its order. Because when you differentiate x cubed, it becomes x squared. This only has two answers at most. So there's quite a lot going on there. I mean, that's a little bit vague and that's probably not explained very much to you, but this is beginning to sort of touch on a lot of fundamental ideas about the shapes of graphs. This being a cubic sort of spoils it slightly because you knew what to expect. In the next example, you probably won't be as familiar with the function in question, and you will actually have to trust d squared y dx squared to diagnose what those points are. So here again, a very similarly worded question. Again, I'm going to be very cautious to make sure I don't lose any marks at the end for finding all the x values, finding out what they are, but not working out the corresponding y values, I'm going to finish up this question with coordinates. If you don't have brackets with 2 entries in them at the end, you know you've got the wrong answer, whatever else you might have done in the question. So in this question, we're dealing with a quartic. Now, there are all kinds of quartics. I mean, if you're familiar with quartics, you could be having that kind of shape, you could be having that kind of shape, you could be having them kind of merging together. Actually, it looks suspiciously like a quadratic. You're not really sure at this point what kind you're going to have. So let's trust the kind of algebra that we've spoken about so far. Let's trust dy dx and d squared y dx squared to tell us. So first things first, I'm asked about turning points. we're asked about turning points, so that's going to be something about dy dx. So I differentiate this expression, nice. I then try and work out that a turning point dy dx is 0, so I set my expression, I set my dy dx equal to 0. If dy dx is 0, you're talking about turning points. If you're equaling y to 0, you're talking about roots. But here I'm talking about turning points. Dy dx is 0. I get this expression here, and I solve that to get x equals 0 and x equals minus 3 over 2. I've just written a wee point of caution here. In solving this, it's very easy to lose solutions. Okay, if you did this before looking at these solutions, you may have only got this answer here. And the reason that would have happened is because you might have divided through by x squared. You'd lose this answer here. Always best to solve by factorising because you don't miss any answers. The reason that dividing through by x squared is wrong is because you know it's forbidden to divide through by 0. Well, x squared could be 0. Okay, so the case which is forbidden is you dividing through by x equals 0. So I've got two answers here, x equals 0 and x equals minus 3 over 2. I know they're turning points, but I've no idea what kind of turning point they are. So I'm going to use d squared y dx squared to find out. So I go back to my expression here for dy dx and I differentiate it again. This is going to be my diagnostic tool for deciding whether they're maximums or minimums, and hopefully it won't fail me. So here, I'm going to try this one first of all, x equals 0. So at x equals 0, the value of d squared y dx squared is 0. So in this first example, it has failed me. I was hoping it would be bigger than 0, meaning it was a minimum, or maybe less than 0, meaning it was a maximum. This thing here has opened all the possibilities. Okay, d squared y dx squared being 0 means it could be a point of inflection. This is the only way that could happen, but actually it could also be a maximum or minimum. So the only way of me finding out whether this point x equals 0 is a maximum or minimum is to investigate either side of it. See what the gradient is doing before and afterwards. So I want to go quite close to 0, but I want to keep nice numbers. I don't have access to a calculator in this exam. So minus 1 and 1 are nice numbers to pick. They are definitely either side of 0. Now I need to just be very cautious for a second that I've not gone too far with this. If I've gone so far that I've gone past another turning point, we've got a problem. Well, here you've got a list of all the turning points. If you go as far down as minus 1, you don't get as far as this turning point here. So we are okay with these two values. Plug them in, and I find that just before this turning point, before it, I've got a positive gradient. We know that that means it's increasing. And if I investigate just after this turning point, I find out I've got a positive gradient. So if you're positive before and positive afterwards, it must be a point of inflection. We didn't know previously it was a point of inflection, but we now do know that it's a point of inflection. X equals 0 is a point of inflection. Now I'm going to investigate x equals minus 3 over 2. Now, just because d squared y dx squared didn't work for this doesn't mean you don't try it for everything else. We're hoping it'll work for this one here. So, going down a little bit here, plugging x equals minus 3 over 2 into my expression for d squared y dx squared. Be very careful with your algebra here. I get 36. Okay? 36 is positive, so this is a minimum. So I have found that minus 3 over 2 is the value where minimum happens. Okay? So I now need to plug back into my expression for y to get the corresponding y values. So x equals 0, we know it's a point of inflection, its y coordinate is 0. X equals minus 3 over 2, we can work out that its y coordinate is minus 27 over 16. And this point here is a minimum. So I've got a point of inflection at 0, 0, and a minimum at minus 3 over 2, minus 27 over 16. I've drawn a sketch here. I'm just wondering, was I asked to draw a sketch? Yep, hence sketch the curve. So down here, I've drawn it. Okay, so this is my sketch of the graph. It goes down, 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 down. I get a minimum. I'm going up. And this is the bit we just investigated. We saw that at x equals minus 1. Down here, it's going up, and it is going up. It pauses for a second at that point of inflection, and then it continues to go up. It's still positive when we plug in x equals 1. We did that up here as well. Okay, so what we can sort of see is that it isn't quite the kind of classic quartic look. What we've actually got is we've sort of got this maximum and minimum merged together to give a point of inflection. I tend to think of points of inflection as a merging between a maximum and a minimum. So one tiny overview, and I don't want to talk for ages of one question, but this question is a good example of this, okay? The value of y tells you how high up or down the graph is. If you plug in an x value and get a big value of y, it means it's positioned really high up. If you plug into dy dx, you plug your x value in and you get a really, really big number there, that means it's going up very steeply. It doesn't mean it's really high up above the axis, it just means it's going up steeply. I mean, there's lots of combinations of things you can get here. If you get a very negative value of y, it means it's really low down. If you get a very positive value of dy dx, it means it's going up steeply. That's perfectly possible. I mean, for instance, down here is an example. There, that's very low down. It's got a low value of y, but it's going up very steeply. So it's got a high value of dy dx. If I investigate this point here, if you plug into the expression for y, you get a positive answer because it's above the axis. It's quite high up. If you plug into dy dx, you get a negative answer because it's going down. If you were to plug into d squared y dx squared, that would be telling you how it's sort of curved, whether it's concave or convex. All three of those things, y, dy dx, and d squared y dx squared, tell you different things. The reason I mention this is because when you're testing either side, you tend to get people plugging into all kinds of expressions here, or even when you're trying to find out coordinates, people don't plug back into the original thing. If you want to find out where something is, you plug in y. If you want to find out how steep it is, you plug into dy dx. So this question here is an optimization question, and it's a very, very important use of differentiation. You should be interested in differentiation just because it's a nice thing to do, but this is probably the main kind of practical or industry kind of application of this. If you're running a business of some kind and you want to make something as big as possible, you're talking about making something a maximum. You're saying, if I had a graph of this, when would it be at a maximum? What do I need to do to make that maximum happen? Equally, optimization can be about minimums. You might be trying to minimize wastage. If you have an expression, a piece of maths that says this is what the wastage is, you want to know the values that you should be plugging in to make that as small as possible. So in these questions, you'll either be trying to make something as big or as small as possible, and you'll be deciding when that happens. There is a lot going on in this, and sometimes the algebra gets people distracted. So I'm going to talk through the whole thing, talk about all the steps I've taken. I'll then go into the details of it, and then we'll talk about the structure again. So first things first is, looking at this question here, it is interested in the minimum possible surface area. This question is about surface area. I want to write down a statement of what the surface area is, and here is when I've achieved that. So there's a bit of work to get to that point. I wanted to write down an expression for the surface area. And a practical point about this is, if you're going to be trying to find a minimum, you're going to be differentiating. You need to have an expression for the surface area that contains only one variable, only one letter. You cannot differentiate something if it has two letters in it. So although we all know this expression for the surface area, I have to go a bit further than that because I can't differentiate it while there are R's and H's going on. Note that pi isn't an issue, pi is just a number. It's written as a letter, but it's just standing in for a number. So, first of all, this is maybe the first thing I should have written down. I'm interested in surface area, and surface area is 2 pi r squared plus 2 pi rh. Okay? Now, I need to either replace r or replace h. So I need a connection. I need to either write h in terms of r or r in terms of h. So this fact here that was given up here, the fact that the volume is 128 pi, I used that to write down what h was. Okay, I plugged it in and I got an expression for s that only has r's in it. Now, I'm trying to find a minimum. Minimums mean that it's a turning point or a stationary point. So I want to find when this is a minimum. Now, people tend to say dy dx, but in this case you're talking about s. You want to find out when s is a minimum. So we're trying to sort of differentiate s with respect to r. R is the letter going on in this. So I'm going to work out what ds dr is and find out when it's 0. When ds dr is 0, I have a turning point. Now, it's not necessarily a minimum. It might be a maximum or a point of inflection, but if I'm trying to find a minimum, ds dr will be equal to 0 at that minimum. So when I work out what ds dr is, maybe a bit tricky there, the differentiation, I get this expression here. I'm setting it equal to 0 to find the turning points. I solve that and I get a value of r out. Okay. At this point, there's all kinds of jubilation and excitement that you've got the answer, but you are not sure at this point. You have found a point where ds dr is 0. You found where the surface area has got a turning point. This might actually be the worst of all situations. This might be a maximum. You need to make sure and you need to show in the exam that it is indeed a minimum. Well, luckily we have a method for checking that something's a minimum. So I work out the second derivative. I differentiate s again with respect to r. I get this expression here. Okay. People start trying to decide whether this is a maximum minimum. This is not supposed to be a maximum minimum. This is an expression which you plug into. You are investigating the value r equals 4. So you plug in the value r equals 4 into this, okay? Without even calculating this, you know that r cubed, or 4 cubed over 5.2, whatever's going on there, that is going to be a positive number. So because it's positive, it is a minimum. The question wanted you to find a minimum, and you've checked that your value of r is in fact a minimum. The guts of the question is done now. Okay, you were asked to find the minimum kind of dimensions of this thing. You found out that r equals 4 is a turning point, which is in fact a minimum. All you have to do then is you then work out what h is. Go back to your initial expression for h. You've got that as well, and you've got your dimensions. The radius is 4 and the height is 8. It ends up being that gives you a total surface area of 96 pi. That is a minimum. I mean, go away, pick other values you want that might work. They might well give you the same volume. They might give you the required volume, but they certainly won't give you a surface area as small as this. Obviously, if you're manufacturing cans or something like this is quite a useful thing because you'll use less metal to get the same amount in it. Okay? So let's go into some of the details of this question. So first of all, I need to know my formulas. So make sure you have those, because I don't think either of them are actually given in the formula sheet. So I've got those two there. I'm interested in this one here, so I rearrange this formula to get h by itself. If you rearrange to get r by itself, you already sense that that's probably not the easy way of doing things, because getting r by itself gives you square roots. It just makes things a bit more awkward. You can persevere with it though, and you'll get the same answer out. So here, I've chosen to make s all about r. So I plugged in this expression for h, where h originally was. Looking at this, the r's cancel down. It's easier to write it as r to the minus 1 because of differentiation in a second. Okay. When I differentiate this, the 2 comes down, decrease the power, the minus 1 comes down, makes this a minus, and becomes a minus 2. When you set this equal to 0, usually if you've got two terms, it's good to bring a term to each side. People can usually spot easier what to do at that point. So bring them to both sides, I cancel the pi's, try and get the r's all together, and you end up getting nice values here. R cubed is 64, giving you r is 4. Good thing that it's not r squared equals 64, because then you get into all your existential dilemmas about whether you can have a negative radius and all that. R cubed equals 64 has one answer, and that answer is r equals 4. So finding the second derivative, well, you don't start from scratch. You go back and look at ds dr and you differentiate again. So this is really r to the 1. The 1 comes down, and the r to the 1 goes away. It becomes r to the 0, which is 1. Here, minus 2 comes down. This makes this back to being positive, and you get this expression here. One thing which is always nice to notice is what d squared s dr squared actually means. Okay, I kept getting obsessed up here with saying that d by dr is something which acts on s. It does something. I said earlier on that this is an operator, or it affects s. If you look at this thing here, what this really is it's saying differentiate with respect to r, ds dr. That's another way of writing d squared s dr squared. It says take what you had, take ds dr, which already was s, differentiate with respect to r, and differentiate it again. So we've done that differentiation, we've got this expression here, and as I said, there's no harm in the examiner taking this little mini shortcut. I mean, well, maybe it wasn't complete necessary. R is 4, so when you cube it, you get 64. You could write this out, but you're never going to try and divide pi into that number. You've got a positive divided by a positive, which is positive, plus a positive, without knowing the value of any of this. This is positive. Because it's positive, you've established a minimum. This bit must be clear. You can't just assume that because you found a turning point, it is the minimum you wanted. Okay? If you went into production with this value and it was the maximum, you're making the worst possible cans you could do. So I've checked it's a minimum, and now you just need to make sure you're answering the question. Just like previous ones where you had to make sure you had coordinates, here you ask for the dimensions. You found r, you need to find what h is. Okay, you want to know what h is, you can see up here there's an expression specifically for what h is. So you plug your value of r in, and you end up getting that the height is 8. So you've got these dimensions here. It didn't really say it wanted the surface area, but you could argue that saying the dimensions it might suggest that, so I just put it in brackets down here to be absolutely sure. The units you get out are the units that you put in. So humour me one more time while I just talk about the structure of these questions, and it's always the same. Okay, so you read the question, you identify what is the quantity you're interested in. Okay, in some questions it might be volume. You want to be interested in the surface area. You must do whatever you can to work out an expression for the surface area in terms of one letter only, and that will usually involve using the fact that they've given you. Okay, once you've got that, you differentiate and say equal to 0, and that is a turning point. Okay, once you've got your turning point, you then have to verify that it's the maximum or the minimum that they're asking for, and that involves doing a second differential. And finally, at the end, you then just tidy it up by working out any of the other quantities they might want.